Welcome to the Center for Gifted Education on Demand Learning, brought to you by Kendall Hunt Publishing Company. Today we are going to look at the science units highlighting what to find. Why Center for Gifted Ed teaching units? Why use Center for Gifted Ed teaching units? Problem-based science curriculum aligns with goals of national science standards and projects. How science systems interact with real-world, social, political, and economic systems, developed by William and Mary Center for Gifted Education, a forerunner in gifted curriculum and instruction. Integrated curriculum model linking content, process, and themes. An interdisciplinary connection. Real-world issues and problems. Supporting habits of mind. Helping to aid in higher-order thinking. Active learning, problem solving, authentic assessments, learner outcomes, learning across disciplines and units, and fostering the 21st century skills of collaboration, communication, creativity, and critical thinking. The Center for Gifted Ed teaching units are recognized by the National Association for Gifted Children. The integrated curriculum model presents students with advanced level problem solving science issues and themes, and help students to understand the concepts of systems through experimentation and demonstration, and also aids in the understanding of how science is related through physical, biological, geological, and/or earth sciences. The William and Mary Center for Gifted Ed science units were developed to be used as a 30-hour supplemental course to a core science curriculum, or could be used for a specialized pull-out science program for the high-ability learner. Depending upon your structure and scheduling, this could be a core unit, or this could be a supplemental unit, which might be a semester long, or with other integrated connections could take the course of the entire year for science. Each of the units are organized around a real-world problem that carefully maps out through specific lessons. And teachers are going to need to be very mindful of the flexibility of perhaps the order of some of the lessons and the number of lessons that a student might need to work through a problem. All of the science curriculum units are centered around problem-based learning. At the elementary level, where's the beach? What to find? Acid everywhere, electricity city. At the middle school level, something fishy, no quick fix, nuclear energy, friend or foe, and animal populations. All of these themes are based around problem-based learning. The Center for Gifted Ed science units were developed using appropriate curriculum to aid in the dimensions for the high-ability student. The units encourage in-depth study of selected content as it relates to a central problem. We know that when students are involved in both experimentation and demonstration, the effects of long-lasting understanding are definitely going to be greater. Higher levels of student engagement, students being able to make connections across units and disciplines, and students' overall understanding is going to be greater with this type of learning. The science curriculum framework centers around a real-world problem. Students will navigate through the understanding of systems by using the scientific research, so they will be able to create their own understanding and solutions to each of the unit's central problems. The overarching goals of the science curriculum are to help students understand the concept of systems, to design scientific experiments necessary to solve given problems, and to study a specific science topic in relation to physical, biological, geographical, and/or earth sciences. The Center for Gifted Ed science units are designed for easy access and implementation for teachers. They are set in 5 parts. Part 1 is the introduction with the content, the goals, unit glossary, material list, lab safety, and letter for parents. Part 2 are the lesson plans. Typically there's about 20 plus lessons per unit. Each of the units is defined with an instructional purpose, the goals, materials and resources needed, the activities, assessments, problem log, notes, homework options, technology integration options, and extension options. Part 3 is the implementation guide. Here you'll find suggestions for learning centers. You will find the templates for the Center for Gifted Ed teaching models. Part 4 is appendices. Here you will find a further detailed explanation of systems, mini lessons, interdisciplinary connections, and rubrics. And Part 5 provides references and resources. There are 2 parts to assessment in the science units. You can look at the portfolio. As an assessment, there may be both formative and summative places for assessment, and the performance base, which tend to be more summative in nature. Through the student activity guide, students are going to be completing problem logs based on a lot of open-ended questions. They're going to be completing some lab reports of their findings. There are some experimental design worksheets and other specific forms that could be used for assessment. This could be part of a portfolio, if you will. There are pre- and post-science process tests. There are a multitude of culminating embedded activities, final assessments, and there is a final concept scientific research assessment. Demonstration and experimentation are both found in the Center for Gifted Ed Science units. Demonstration is really the idea or the concept that is being illustrated. It really serves as a springboard for further experimentation. Experimentation is the part of students that are actually experiencing the science. It's a place for inquiry, it's a place for hands-on learning, and it's a place to address the higher order thinking skills. The basic components of experimental design all center around a central problem, issue, or question. A hypothesis, the variables involved, trials, research, results, and conclusion. Problem-based learning, students will focus on a central problem or issue or question. And through that, they will be demonstrating, they will be involved in inquiry, experimentation, so that they can come up with findings and solutions. Problem-based learning is an instructional strategy. It capitalizes on student and community interests. It provides motivation. It builds self-efficacy, confidence, and autonomous learning behaviors. Some of the features of problem-based learning are as it relates to real-world problems. The teacher is more of a facilitator or coach. There's a strong emphasis on collaborative teams. There is a lot of metacognition, thinking about their thinking. There may be alternative assessment, and it embodies the scientific research process. Problem-based learning always focuses around an ill-structured problem or question. And the students are going to navigate through their research and their findings to come up with some possible solutions. The teacher is really acting as a coach, and the students are participating in experimental design. Ill-structured problems as a part of problem-based learning are intended to be ambiguous. There is no single right answer. The data set is often incomplete. The definition of the problem often changes, and the information often changes and or grows. There are stakeholders to consider in ill-structured problems, and there is usually some type of deadline for a resolution. To summarize problem-based learnings, there is an introduction of a problem, There is reviewing of research. There is the definition of the problem, the research for the problem and a resolution, the actual reviewing of the research, the building of a resolution, and the presenting of a resolution. We're going to highlight one of the Center for Gifted Ed Science Units, What to Find for grades 2 and 3. And there are 4 major goals: to understand the concept of systems, to understand the principles of archaeology, to understand and apply the principles of experimental design, and to develop reasoning skills with application for science. What to Find is a very high energy, high level of engagement for students, participation in problem-based learning. The students are going to explore the field of archaeology. The students are really going to be put in the role of a junior archaeologist and a research museum and discover that construction work has been halted on a new school because historical artifacts have been discovered. The students are going to determine whether or not to continue the dig and build the new school or to halt until they can carefully sort out the historical artifacts. Some of the lesson sampling for What to Find: Lesson 3, Introduction to the Problem. Lesson 6, The Scientific Processes and Archaeologists. Lesson 10, Cultures and Artifacts. Lesson 17, A Simulation Dig. And Lesson 20, A School Subproblem. Keep in mind that students do have a student activity guide to record their findings and to have a place for reflection of their understandings. As part of Lesson 3 in What to Find, an ill-structured problem has been presented to the students. You're a newly hired assistant at a small town that has just opened. It's your second day on the job, and you have learned from the museum's archaeologist has resigned. Later that day, the museum gives a call from a local construction site. While digging to lay a foundation for the new school, a backhoe operator uncovers numerous artifacts. The construction company has stopped while workers wait to hear what should be done next. And this is where the problem-based learning will go into effect. Some key questions to help students in the brainstorming of finding solutions to a particular ill-structured problem. What do we need to find out? What materials do we have available? How can we use these materials? What do we think will happen, our hypothesis? And what will we need to observe or measure in order to find the answer to our scientific ill-structured problem or question? The Need to Know board is a great template for students that are participating in problem-based learning. After an ill-structured problem has been presented, they need to focus on what do we know, what do we need to know, and how do we find out. Teaching the concept of systems is a very important part of problem-based learning. The goals are to ensure that students understand that systems have identifiable elements, that systems have definable boundaries, that systems have inputs and outputs that are based upon those boundaries, and that interactions of systems elements with each other and the response to input from outside the system often combine and determine the overall nature and the behavior of such a system. Understanding the vocabulary of a system before students interact with an activity that involves systems is extremely important. Perhaps some mini lessons on vocabulary development to help further understanding of boundary elements, input, output, and interactions will help to aid in student success. The Goldfish bowl is a great diagram for students to use as a visual for understanding systems. In Lesson 10, students will be interacting with cultures and artifacts as it relates to the elements, the interactions, the inputs, and the outputs. At the conclusion of students defining a system, it is most important that they are able to formalize a generalization. A generalization might be the interactions and outputs of a system change when the system's inputs, elements, or boundaries change. These may be a part of their problem log. This could be a part of some further activity, discussion, and or demonstration. Throughout the science unit, students will also be working with the reasoning model and the elements of reasoning template. It focuses around the critical thinking of the 8 elements of reasoning, where students have an ill-structured problem or issue, and it helps them to guide their thinking, their research and development, and assumptions, and coming up with some implications, consequences, and or solutions. The Center for Gifted Ed Reasoning model focuses on 8 elements: the issue, the purpose, the point of view, assumptions, concepts, evidence, inferences, and implication and or consequences. It sometimes is often useful for teachers to propose a situation or problem that perhaps is of a school or community interest, like maybe a longer school year or homework, and allow students to interact with the reasoning model to give them a little practice before they actually start into one that relates to a specific ill-structured problem and or lesson. This is the template for the elements of reasoning. It serves as a great visual model for students, but it's not necessarily meant to be a graphic organizer that students just fill in. This really can be implemented in a number of ways, and I would certainly give latitude to students as to how they wanted to demonstrate their elements of reasoning. It is often helpful before students begin actually participating in a elements of reasoning model that they have a little mini lesson of vocabulary development. Assumptions, evidence, inference, concept, and implication. Those are pretty big terms, particularly for second and third graders. So some vocabulary webbing, any kind of activities you wanted to do to help further strengthen their understanding of these terms will be very helpful before students actually participate with the elements of reasoning. In Lesson 20, students are going to read a letter from the superintendent and the findings from the dig versus the construction of the new school. Students are going to use the reasoning about a situation or event template, and they are going to come up with a resolution whether or not to continue to dig. The template for reasoning about a situation or event can be a template. Students can demonstrate this using chart paper, pictures, words, electronic devices, but this is a visual for students. They're going to think about who their stakeholders are in the dig. They're going to think about the point of view of each of these stakeholders, if you're talking about a construction worker versus the superintendent versus maybe the community. They're going to look at the assumptions of each group, and then they're going to move to the implications of the views. With that, there will probably be some kind of follow-up reflective writing piece and or presentation as to the initial ill-structured problem to dig or not to dig. The Center for Gifted Ed units encourage a lot of critical thinking for students. Convergent thinking is where a person looks at a particular problem or issue and comes up with some kind of answer. This is particularly appropriate in science and math and technology. Divergent thinking is where students take on a stimulus or a situation or a problem, and they come up with an elaboration of what-ifs and or a multitude of possible answers and or solutions. Problem-based learning definitely cultivates divergent thinking. Evaluative thinking is another level of thinking that the Center for Gifted Ed units definitely foster. Just as we were looking at the situation or event to dig or not to dig, the students definitely had to make value judgments. They definitely had to inquire and defend and or justify their solutions and or choices.
Thank you for your participation in the William & Mary, the Center for Gifted Ed Science presentation. We hope that today's presentation has provided you with an overview of our science curriculum, as well as implementation tips, our models and structure. If we can be of further service, please feel free to contact one of our account managers